So it's my great pleasure to introduce Eric Horvitz, who is Technical Fellow and Director of all of the Microsoft Research Labs worldwide and my manager. Eric is a real world-renowned figure in artificial intelligence and machine learning. I mean, he's done work in machine learning, perception, natural language processing, decision-making, human-AI collaboration, cognition. Eric is not only a computer scientist with a PhD in computer science from Stanford, he also is an MD in neuroscience. I mean, I know very few people in the world who have that much breadth and depth of knowledge. He's a winner of the Figgenbaum Prize, Alan Newell Prize. He's a fellow of the National Academy of Engineering, ACM, AAAI, the American Academy of Arts and Sciences, and he's an absolute pleasure to listen to, so I won't stand between you and him. Here's Eric for you.
Thank you very much. Let me have that forward. Well, it's a pleasure to be here in India, in Bangalore. I spent 3 days, had a fabulous time at the lab, and now coming up and visiting with you here. It's a pleasure to greet you as academic colleagues. Microsoft is in its 27th year now, and the mission has remained the same for 27 years. The primary mission: expand the state of the art, with or without regard to Microsoft. Of course, the second mission there is transfer technologies and innovations as fast as possible. Keep Microsoft vibrant. But the first point here is all about the fact that we're interested in the science and the frontiers, both theory and practice, and by being worldwide an open research model, we reach out to academics like yourselves and students, and we hope there's also reach in, and that keeps us really fresh and keeps the best ideas in the mix, in the melange at Microsoft Research. We just added a new lab, Microsoft Research Montreal, and it was in the news this week. President Trudeau just made an announcement, Prime Minister Trudeau in Canada, about the lab and some reverse brain drain for Canada, in this case from CMU moving into Montreal. So that said, the reason I came to Microsoft was, even in 1992, my discussions with Bill Gates and Nathan Myhrvold, the founder of MSR, were all about intelligence, building computers that can hear, think, question, engage, see objects. PCs might do this someday, Bill thought, and we should really start working on this. And it's always been a major pillar at the lab. I've heard people yesterday discussing what is AI. I like this definition of artificial intelligence is the science of pursuing computational mechanisms underlying thought and intelligent behavior. If you look back to the proposal in 1955 by the founders of the field, somewhere in their first couple paragraphs they said, we're trying to find how to make machines solve the kinds of problems now reserved for humans. And they also pointed out in those days there were 4 pillars of assault on the challenge. They called out perception, learning, reasoning, and natural language. The latter in particular being pointed out as being uniquely human and saying something deep about intelligence. Now, over the years, there's been a rise of a rich set of subdisciplines all within the AI family surrounding these 4 pillars in a variety of ways. And while we tend to hear, as the public and even as researchers, about the big wins, we hear about Watson and Deep Blue in chess and the driverless car with what the Google car is seeing, and recently the AlphaGo work. But in reality, the research has continued, and there have been a stream of results over the decades. For example, at Microsoft Research, our teams worked with the operating systems group for over a decade. And under the hood in Windows, we have machine learning and decision theory being used to guess what you're going to do next at any moment, and prefetch and pre-launch applications to speed things up in magical ways, for example. In the United States, in the 90s, we introduced automatic handwriting recognition into rich pipelines with language models to begin scanning handwritten letters. Those are dwindling, thankfully, but there's still quite a few of them. But 25 billion letters per year being handled by AI systems in the United States and of course now worldwide around the world. These aren't necessarily celebrated in the press like AlphaGo, but the point is that this is not new. There's been an ongoing stream, and we've been learning and learning over the years. Now, that said, we have had in the AI community inflection points. And one of these inflection points happened around 2009 and at Microsoft Research when Jeff Hinton and his group visited us and tried again, and Jeff Hinton never gives up with his team, his use of these layered deep networks. He used to call them deep belief networks, these convolutional networks. And now with the discovery that the same methods that we used in the late 80s, essentially, were actually more powerful than we thought. They were just famished for data all this time. And with speech, we started playing with in our speech team, with the switchboard data set, which is low bandwidth conversations on telephone lines. And just last year, we hit human levels, and now our teams exceeded human levels of transcription in speech. It's not just in speech. The same methods also in vision. Our Beijing team with building with Resonant systems that could see better than humans in terms of categorization on one of the ImageNet classification tasks. And I just mentioned just now reading comprehension. Just last week, the first results came in where both Alibaba and Microsoft Research being a bit ahead, showed that they could actually do better than humans at answering questions based on Wikipedia text in what's called the Reading Comprehension Squad Challenge. Now, with these kinds of successes, companies like Microsoft, academia, academic colleagues, other competitors to Microsoft, Google, Amazon, Facebook, are pressing these advances into service. So, for example, we now have what I would consider magic just 7 or 8 years ago, real-time speech-to-speech translation in many languages in Skype. Tools coming available now that let programmers call cognitive services doing vision in the cloud to recognize faces and emotion and objects, for example. And then products like the Office product line, Cortana, for example, now reading email and extracting, for example, promises you make to other people and requests that are made to you and remind you about them by place, time, user, and location. There's so much more opportunity ahead to apply these methods, even today's methods. I've often called AI the sleeping giant for healthcare. By the way, it's still asleep. There's so much to be done, again, even with today's methods and yesterday's methods that have never been pressed into the service that they deserve. For example, the system we built several years ago that's distributed in hospitals throughout the world, computing the probability that a patient will be readmitted in 30 days from thousands of variables right from electronic health record data, and machine learning going on locally at every hospital, because every hospital is a bit different. But the model here used in that healthcare area of taking sense data, going to predictive models, going to decision models that know how to manipulate costs and benefits, is a powerful pipeline, golden pipeline that can be applied in many, many fields right now, and not just for automation, but for education, recommendation, and insight building as well. And I'd be remiss if I didn't talk about scientific understandings coming through the lens, the computational lens of artificial intelligence. Daphne Kohler's team several years ago showed how you can take the Morse code of gene expression data and through probabilistic modeling methods developed in the uncertainty community, generating modular designs or seeing the modularity of biology and how things worked when it came to regulation. And I think in stunning work, I have to celebrate Sarah Jane Dunn and her team's work at our Cambridge lab in unraveling mysteries of embryogenesis. How does a little ball, a little fertilized egg become a human being, roll out? How do stem cells become different tissue types? It seemed like a big, complex problem, but applying Z3, that many of you know is an AI theorem prover used in verification and other places, figured out the code and found that stem cells go to tissue types with 3 control points. This was an AI problem and insight building here. So that said, let's say, where do we go from here? About 8 months ago, we formed a unit called Microsoft Research AI at our main research center in Seattle. And the basic idea behind doing this was, back to our 4 pillars here and our subdisciplines, Microsoft Research has been an open lab. We've always, across our 8 sites, have hired top talent in different areas, these subdisciplines of AI. And the thought was, given where we are with artificial intelligence, and by the way, even with these inflection points, my view is that things have been moving very slowly. I think that if we showed people where we were today in 1955, they'd be severely disappointed. I don't know, Raj, can you vouch for that? I mean, we expected so much more. But we can do more, we believe, even given the platform we're at right now. So here's the kind of the dream sequence in putting together Microsoft Research AI. Let's crystallize. Let's bring together these teams in a new way and think about a set of shared aspirations that we can all organize around, and then organize all of our resources and planning around. There are actually 5 aspirations. I'm going to talk about 3 today, given my limited time. Number 1, attain more general intelligence. Second one, master human-AI collaboration. And the third, pursue insights and possibilities with AI people and society. Let's talk about attain more general intelligence. If you think about it, we've become quite good at building idiot savants. These narrow wedges that we celebrate, yes, we can use them in object recognition. We could run a translator. Maybe we can get a question answering system to work. But these aren't the kinds of intelligences that the founders of AI sought to build someday. We like to address what I would call an understanding and pursue an understanding of the mysteries of human intellect. What are these mysteries? How do we learn in an unsupervised way, even as toddlers? Massive amounts of information and understandings and knowledge. How do we come to understand common sense of the world? Gravity, containment, the common sense of social discourse. How do we apply and solve many different kinds of tasks in daily life from one to the other that seem quite different? In some ways, you might say that we've become masters at building wedges, narrow wedges of competency, and we want to go to richer integrative intelligences. One way to look at this is, one perspective is combining even the competencies we've been able to develop to date into symphonies, well-coordinated symphonies of intelligence. So as one example here, one project we call the Integrative AI Project. One of the projects in this area is called the Situated Interaction, Situated Intelligence Project. We're trying to combine natural language, dialogue abilities, vision abilities, social discourse, common sense, the common sense of space and time and engagement, and interaction abilities to build new kinds of experiences and to also understand what it takes to coordinate among these competencies. Turns out that there's some magic, we think, in the actual coordination and using machine learning to coordinate multiple components, each of which is developed separately, pulling together these modular abilities into a unified whole. In some ways, doesn't it seem like we're singular intelligences as people? We're probably not. We're probably thousands of competencies coordinated with such fluidity that it feels like a bright singular intelligence. Now, another area that I'm just going to give you a couple different set of directions for what we're doing in this general intelligence pursuit area. Now, we all celebrated and we're all very excited about Deep Blue in chess, and later poker. I mean, in the AI community, we actually solved the game of checkers fully, for example. These interesting games of perfect information where the magic behind a lot of this is we can actually run simulations with perfect state information trillions of times and collect data, as you all know, and then use machine learning to learn value functions, learn moves, and start playing at better than human levels. But this doesn't apply to the real world. We don't have, we're in a very, very data scarce situation, even if you believed in the power of machine learning to learn some of the nuances of life. One approach is to sort of think about what's the analogy for richer worlds to playing trillions of games against oneself and learning how to solve those problems. And it's building rich simulations with an eye to data collection. So AirSim project, Shatal Shah and Ashish Kapoor and others on the team have really tried to build a system with rich physics, friction, lighting, and to take actual high-fidelity implementations of sensors as they exist, for example, on a drone, and model them too, so we would see what an actual drone would see in this world. The messing world, the crashes, and so on. And one example is we can actually begin to learn. So we made a very clear decision to have data collection harnesses in these simulated worlds because it's all about machine learning. And for example, if we run a stereoscopic cameras in this world and we actually start computing distances from them, since we know ground truth of depth, can we build a convolutional neural network from the data streams from the simulated world and then begin using it in the world and show how well it would work in the actual world, and then worry later about the difference between the fidelity of the simulated world and the actual world, the open world. And so once we can do that, we can even start doing reinforcement learning in these worlds. So as an example, and I'm moving to driving here, this is a reinforcement learning system trying to learn by itself how to drive. And you're going to see the first 10 of trillions of runs where the car becomes brilliant over time because it's learning about driving in the world with an objective function using some basic principles of reinforcement learning. It's getting better and better even in real time here. Now here's a really cool example of where we showed, I don't need all that sound here, where we showed how we could train up a drone to start doing the task of inspecting power lines without crashing into them. So after thousands of training sessions, we have this beautiful system we can now deploy in the world, we think, to, in remote areas, make sure the power lines are all doing well. Again, trained on the sensors in this world and then are running. So just one direction, again, building it and collecting large amounts of data in simulated worlds. Let's talk a little bit about mastering human-AI collaboration. Over the years, my colleagues have almost, we say the hardcore AI planning colleagues have said, well, why do you play with human interaction, that HCI stuff? My reaction has been reasoning and decision-making in ways about what people are trying to do and recognizing plans and trying to help them is harder than playing chess. It's harder than a Go move. And it's a really hard, formal, interesting area that mixes decision-making, learning with design, and social affordances. So what are some components and some directions in this world? I want to just inspire people to work more on these interesting problems to basically build systems, AI systems that can actually augment and extend human beings in a variety of ways. Well, one approach is to use AI to develop new kinds of engagement models directly, new kinds of perceptual abilities. So in our Cambridge lab, we built systems that actually use generative models. These aren't videos here, but this is actually a system that's recognizing at a distance human hand pose and gesture. I've often said if you can get thumb and forefinger into the world, digital world, you can build civilizations. So if you want to see what people are saying and doing, how they're engaging, wouldn't it be great to have computers that recognize us at a distance? But let's talk about cognition now, moving from perception to cognition as another piece of the important recipe of building systems that can augment human intelligence. I like viewing 20th century cognitive psychology as characterizing human blind spots and biases and gaps in our abilities. So if you look at the human abilities as this y-axis here and this blob with gaps as the kind of cognitive artifice we all share essentially, even though we're all different in our own ways, we have almost untapped knowledge in AI about the detailed biases and gaps and blind spots of humans. And here's, again, the dream sequence. Might we build systems someday that are explicitly designed to fill those gaps? And we have areas of psychology in memory and attention and judgment. We can start, and we have at Microsoft Research, leverage these results and machine learning and sensing to actually design custom-tailored extensions in different areas for different kinds of tasks. Now, you can start straightforward and do some very basic things. About a year and a half ago, I was very happy to see this Chameleon Grand Challenge, which basically provided the AI community with thousands of slides with the correct answer: is there metastatic breast cancer in this lymph node? The Chameleon Challenge here. Now, humans were superior to the best deep learning system. The deep learning system was the best, but humans were superior. But when you combine even a naive way, when you combine the output of the deep net with the human, you cut down errors significantly. Just running these together, right? And these were experts that were better on their own than the best system. Here's another example in the crowdsourcing world from our team with Ajay Kumar. There's a challenge to help the astronomers recognize and tag hundreds of thousands of galaxies of different types with human eyeballs. Right? There's so much data, the astronomers need help from citizens. And so it turns out there's a system called Galaxy Zoo where people are looking at this data, these galaxies, and tagging them, volunteers that are called citizen scientists. We also could apply machine perception to the same problem, and in about almost 500 features, analyze each of these galaxies. Well, it turns out when you actually use machine learning to figure out how best to weave computer vision with human intellect, human perception, you could figure out when to call humans, how they should help, and how many people you might need to vote, for example, with labels, and go to full accuracy with half the human effort in the right way, or 0.95 accuracy with a quarter of human effort. And this was combining machine learning to figure out how to do the weave with a planner that could sort of guess ahead in an AlphaGo style sense, looking ahead in a non-myopic way to compute the value of human contact, human reasoning, human perception. Another really interesting area in the complementarity realm is human errors. Several years ago, we took a large amount of medical data from emergency rooms, and we defined a surprise, a human surprise, a surprise of an expert physician as an emergency room doctor tells the patient to go home, they're fine, and within 48 hours they show up at the hospital again, and they're admitted to the hospital, which is a serious issue. They're admitted as an inpatient with a serious problem that was not encoded anywhere on the chart when they left. That's called a human surprise. Well, that's an interesting training signal. And if you had massive amounts of data, including the surprises, you can actually compute a system that will infer in real time medical entities that hide in the shadows of expert cognition. And then we could tell our doctors, we've built a model, not that's going to replicate humans, but it's been trained on the frontier of your knowledge, on the illusions that you face daily, on these dangerous errors that you'll make in the hospital. And at discharge time, the system, as the physician's writing up the discharge notes, the system might come forward and say, hey, I got a couple things that might surprise you about this patient. Do you want to see what I'm thinking? This is a very powerful complementarity. By the way, I should say that in the United States, in-hospital deaths due to human error in the latest report make it the third most common cause of death in the US, over 250,000 people per year. You can see why I say AI is a sleeping giant in healthcare. Might these systems be like the safety nets that catch bridge workers someday when they're working on bridges, just in case they fall as they're painting the bridge or putting in a rivet someday? And isn't this an interesting application of AI systems? Now, the last piece that's very important, I think, in thinking about how to build systems to help human beings is this idea of coordination of initiatives. So here's our complementarity of human cognition and machine intelligence. But we want to think about, in a real-world setting, what's the design and the control of the mix of initiatives, right? And let me show an example here that makes it very, very concrete from my colleagues at Johns Hopkins. I sit on their advisory board, and I've been following the work over the years, Greg Hager and team in surgery. So Carol Riley, a number of years ago, for her master's project, working with the Johns Hopkins robotics team, built a system that could look at surgical videos and that could understand different, what you might call actions in surgery, to build a grammar of surgery that could be recognized. So did quite well at recognizing different actions, a tightened suture, a loosening, a left transfer. These are the phrases surgeons use when they talk about their surgical actions. And then you can take this ability to detect state, to recognize surgical plans of a human surgeon, And then imagine someday, what would it be like for a surgeon in manual mode to work with an AI system that's looking over, that's going to assist hand in hand in a back and forth volley of a mix of initiatives. See the auto mode here now. You imagine you also have some UI conventions. When is the system automated? When is it not? Here's the manual mode, inserting this suture needle into a, thankfully not a patient, but some sort of cookie dough, practice dough here. And you'll see how automatically now the system understands how to grab it and pull and tighten. This is the first wee hours of a coordination between human and AI robot in surgery someday. Now, initiative is also interesting in human-computer interaction. I'll just watch this interaction here by the receptionist that I have by my door at Microsoft. Watch the facial expressions being controlled by the AI system. We have the audio here on this.
Looking for Zach?
Yes.
Are you here for the 2 o'clock meeting with Zach? Sorry, did you say you were here for the 2 o'clock meeting with Zach?
Yes.
Is one of you John?
Yes.
Sorry, I can't tell who is speaking when you stand so close together. Which one of you said they're John?
I did.
Right. Hi John, Zach is expecting you. Will you be joining the meeting? Sorry, will you be joining the meeting?
Yes.
Alright, I've let Zach know you'll be joining his meeting with John. I'm sorry. I think Zach is running a little bit late. I'm pretty sure he's on his way.
There are 4 layers of uncertainty in there, and before we built the current models, they're all just entropy measures. Now they're controlling gestures, gaze, when the system's coming forward. There's a lot of subtlety to that system. Let's move on now to pursuing insights, possibilities with AI people in society. I wanted to start now by talking about some of the dimensions here of the incredible opportunity and challenge ahead here, and start with leveraging AI in societal challenges. Again, sleeping giant material again here on possibilities. So I'll show a couple of examples that really I found inspirational in my own work with students over the years and colleagues. So there's an interesting application of machine learning, decision-making, and planning when it comes to large-scale public health epidemics, for example. Cholera is a disease that will kill about 100,000 to 150,000 people per year around the world. A few years ago, Kira Rudinsky and I said, let's take a large amount of data about historical data going back 100 years, looking at cholera epidemics, and look at DBpedia for detailed information as to where they happen geographically, look at the weather feed and so on, and we've learned to predict in advance high-risk regions for cholera next year, this season, and discovered new things that we took to the actual epidemiologists. Like, for example, we discovered that a very long dry spell in a region that's then hit with a flood is at much higher risk than normal years of hydration for a variety of reasons that we're still looking at and trying to investigate with experts in cholera. But here's the thing. If you can get fresh water to a cholera patient, someone suffering from cholera, you can cut the mortality rate from 50% down to like 1% or less. So the idea is to predict in advance where cholera is going to be and make sure you have fresh water at those locations, even if it's expensive to do that planning. And now there are very short-acting vaccines, and the Gates Foundation and other groups want to know they're expensive and short-acting. Where should we take them and when? If we can compute and infer based on weather patterns and structure, we can do a great job with that. One example. Here's another example. People with special needs, like sight impaired. And this is getting into the Seeing AI system, which you may have heard about. And the idea was, can we take, again, those wedges we have of different kinds of abilities to see objects, to caption photos, to caption imagery, to recognize friends and their emotions, to actually speak text to speech, to scan barcodes and understand products in stores, might we start addressing the special needs of sight-impaired people in one package? It was interesting, this project started out as a hackathon project. His Saqib, who was a developer in our London office, and he made a comment once that it'd be really, one thing he doesn't like being sight impaired at developers meetings and with program managers and so on at Microsoft was he doesn't know if people are listening to him when he speaks. And so the first goal was, let's build a system that lets him understand who's sitting in front of him and their emotion. And it was a really big deal to him to have this ability. And that's what led to the richer system called Seeing AI now, which is now available as an iPhone download. There's so much to do for AI for Earth in general, thinking about sustainability. Many different directions here. In the United States, the National Science Foundation has funded several different terms of what's called computational sustainability, looking at challenges, for example, like how do I ideally set up a reserve that would do its best to protect wildlife in a city region. Here's a project I want to talk about because I think it really stresses the power of being creative and leveraging existing data streams. So it turns out right now over the United States and over India, in South Asia and other places, China, if you look up in the sky, there are thousands of flying sensors at this moment. And back when Ashish Kapoor and I started looking at this problem, we realized we can actually go to services that would tell us information, ground radar trails on each of these airplanes flying at any moment. And we wondered, can we build a weather map from these thousands of sensors? Now, the United States NOAA agency, which does the weather maps that the planes use and they plan based on and the weather people on TV use and so on, launched just a few tens of balloons every few hours around the nation. And it's a very, very sparse set of sensors they build their map on. It seemed much more high fidelity to basically think about the geometries, think about the graphical models, and think about how to convert and harness these thousands of sensors for our goal now of inferring wind speeds over the nation. So if you go to this true cloud service, I paused for a little giggle there, called WindFlow, windflow.azurewebsites.net, you can see what NOAA says about the winds over North America and see what WindFlow says. And it's often quite different. And we have good information that WindFlow is quite a bit better based on a traditional holdout set analyses. But also, we had a fun chance that I'll share with you a bit of launching weather balloons in eastern Washington, for example, and to really get ground truth on where balloons would go based on wind flow. So we'd call in the FAA, we'd say we're going to fly a balloon today, it's going to be going very high. You have to register and report these balloons to the FAA. By the way, these balloons go so high, I'll share some beauty with you. You see the curvature of the Earth, which is really nice. But look at what our wind flow model told us and what NOAA says here. And we were only 12 miles off, and NOAA was 56 miles off. This shows in general how much better we do with multiple launches here. And we're now working with a major carrier to use our winds. They're pointing their onboard planner at wind flow as opposed to NOAA to do better routing of their planes with lower CO2 footprint. And this same work was leveraged to build a richer hybrid weather system later by someone, Aditya Grover, who went off to Stanford. He was a student, high school student, college student, pre-doc from India, working with us. Here's another example from several years ago on leveraging existing feeds with AI techniques to learn about people in situations where there's an opportunity for recovery from a disruption. The Lake Kivu quake was in the Democratic Republic of the Congo in 2008. And we ended up getting access to cell phone data, just ins and outs from cell towers from Rwanda, which was a country adjacent to the Democratic Republic of the Congo. Just 140 cell towers, these dots in this Voronoi diagram we had access to, literally just numbers of calls in and out of those cell towers. Based on that, 3 years of data, we could listen for anomalies of people using the phone more during a time when there might be something surprising going on, like the ground shaking. Combining that with a model of dispersion from an epicenter, we were able to actually infer just a few tens of kilometers off where the epicenter was, 17 miles off, by converting the cell towers across Rwanda into an array antenna, looking at the bumps over every single one of those antennas. Then we can compute where is there a disruption going on in Rwanda over time and how is it persisting weighted by the population levels, and even use a decision theory model to say, take the current uncertainty, a coherent measure of uncertainty in our inferences, and compute an ideal reconnaissance plan to learn more. All from existing cell tower ins and outs, taking that smart lens of AI on that data. So before summarizing, I want to talk a little bit about some of the downside and rough edges with AI right now that are posing some interesting opportunities and challenges to thinking through some of the upside of the fruits of machine intelligence. This includes the whole area of trustworthiness and safety of our systems as we come to rely upon them more, especially in high-stakes areas like healthcare and transportation. The area of fairness, accuracy, and transparency, which is coming to the fore now. It's interesting how just a few years ago we were so excited to get like a classifier running in a healthcare setting, or a predictive model, even in criminal justice, to be helpful. And now we're stepping back as a community with whole workshops and rising areas of scholarship in trying to understand how can we detect when our systems are leveraging implicit, sometimes very subtle but powerful biases in the data about gender, about race, about criminal propensities from data sets that might be doing injustice to society because they will, at low cost, fuel vicious circles. For example, if you have a lot of policing data gathered by looking at this side of the tracks because of concerns with the broken windows on this side of the tracks, the broken window policing as it's called, and then you apply this data set somewhere else, you'll tend to replicate falsely the demographics based on the assumptions made as to where the first sensors were focused. And at a place like Microsoft, we field cognitive services. We want to develop policies and formal metrics for detecting bias and for debiasing systems. And it's not for the faint-hearted, this task. It's a very interesting technical challenge, and also it's context sensitive. If I didn't include gender in a medical reasoning system, it'd be malpractice. However, if I fold gender in inappropriately in a resume recommendation system, I'm doing a disservice by amplifying a bias that we don't like to see in our inferences. The area of transparency is coming to the fore now. I often say it's interesting, and Raj Reddy will remember this, back in the expert systems days, explanation was a major topic. There were whole dissertations. Randy Davis did a whole dissertation on how do you explain the reasoning in a production system. Explanation was considered critical. And we're coming back to that now, saying, wait a minute, how do you explain an inference to somebody who just had their loan rejected as to why? The Europeans, within 2 months from now, have told us through a regulatory action and document known as GDPR, that we better be able, we as providers, whether we're academics or industry, as providers of services, we better be able to describe what they say in a clear way, the logic of the processing behind important decisions made by automated systems. Jobs and economy, we'll just leave that for a discussion point maybe in the panel this afternoon. There's an ongoing debate, which jobs are going to go away, how disruptive will AI be as we get into the science and capabilities of human intellect? Won't we remove some jobs that we relied upon, and maybe even jobs that are this time around in very, very high-paying sectors like pathologists and radiologists and certain kinds of other diagnosticians, as well as truck drivers, for example. A major fraction of the United States, I discovered, is supported by truck driving as the primary source of income. Others point out that just like any other technology, AI will create new constellations of opportunities to work, new kinds of jobs, especially if we get that augmentation right, augmenting human intellect to create new kinds of productivities. So on this interesting area of AI, people, and society, we set up a board called the AI and Ethics in Engineering and Research Advisory Board at Microsoft, reporting to Satya Nadella and the SLT, or the senior leadership team, that is working now with representatives from every major division to come up with policies in safety and transparency, labor and economics, and issues around bias and fairness, as well as standards of practice for human-AI collaboration more generally, how these systems work together. I should say that we just published a book. It was a collaboration of Microsoft Research and our policy group last week, and it's available for free download right now. Satya Nadella and Harry Sherm wrote a forward to this book, and it captures some of the thinking coming out of the Ether committee right now, where things are headed at Microsoft Research. And finally, I want to make a comment that we can't do this alone. So Microsoft worked very hard to bring together an organization known as the Partnership on AI to benefit people in society, or just PAI. It was fabulous working. I'm chairing this board right now, but we brought together Amazon, Facebook, Microsoft, Google, DeepMind, and Apple, all to the same table, where we decided, let's come up with best practices for the community when it comes to these rough edges of AI for a better future. So I'm going to stop by just summarizing pathways ahead for AI. We need to amp it up on pursuing principles of intelligence. It's exciting, yes, but we haven't made much progress if you look very carefully. And you put the hats on of the founders of our field. We want to harness AI to augment human intellect and empower people to achieve more. This is a whole area in itself that requires focus of attention and technology. We want to work to solve societal challenges, as well as address rising ethical issues with AI, especially when it's applied naively. And there are some surprises and twists and turns there that are coming to the fore that we didn't expect about even 10 years ago. And it's very important that we collaborate widely on technology and policy and engage multiple stakeholders in industry, academia, policy, civil liberties organizations, and the general public. Thanks very much.
Thank you, Eric. And I'm sure there must be questions that you would want to ask Eric. So if there, yeah, most of us, can you get the mic, please? Yeah, wait for the runners to give you a mic, and then you can, before that, you can raise your hand so I know who has a question. So yeah, that's the next one. Yeah.
Thank you, Eric. Hello.
Hold it down, hold it down, hold it down.
Okay.
Yeah.
Yes, it is working now. Really, thank you very much for a fantastic talk, just going over the history as well as the future. It looks like a great future and lots of opportunities. I wanted to delve deeper a little bit into the ethics question that you alluded to. I think that's a question I have thought about, and I have had no answers. As you said, it is not for the weak-hearted because so gender, for example, or the race, there are lots of correlated variables in the data set. You know, we have known that if you use zip code, then it is it's a proxy for race. If you start using maybe your grandfather's college degree, that becomes a proxy for race, or whatever. There are many, many other variables. And if we start to remove all such variables, then we will be left with nothing to be able to really make a useful prediction. So I'm curious where we are in terms of sort of solving some of these issues, because they look incredibly hard to me, and I don't even know how to start.
Yeah, no, these are very good questions. We just we're doing deep dives at Microsoft. As some folks might know, at several of our centers, New York City in particular, our New England lab, as well as Redmond, have significant efforts in this area that's called FATE and FAT-ML. It's actually a workshop called FAT-ML, Fairness, Accountable, and Transparent Machine Learning now, where people are developing methods, and they're showing, for example, some methods for, let's say, debiasing and detecting and debiasing gender bias in large-scale vector representations of language, for example. And they also show trade-offs, like we can actually do this measure if you try to fix the challenge with nurses are women and doctors are men, and you take these obviously biased, nuanced dependencies and neutralize them by stretching these spaces in different ways, that you induce errors of various kinds too. And so it's going to be a kind of a trade-off at times where, or at least being transparent, right? You know, if you detect a problem, you can say there's a problem with this data. I want to point out, by the way, it's not just nuances of bias. There are legal issues. in the United States and probably in India too, there are laws about anti-discrimination laws where you can't discriminate by gender in certain situations or by race. And so systems that are doing that, it can be formally called breaking the law. And there will be court cases based on these and people bringing these issues to trial and to judges and to juries. So we need to develop methods to detect, characterize. If we can't fix, at least disclose. If we can fix, characterize the loss and accuracies we're getting by trying to balance out the negative biases that might be detrimental to society. But it's a challenging area. And I have to say that I hear you're coming to Seattle this summer. We should actually talk more.
Okay, we'll take one question there at the back. Yeah.
Humankind recognize real and fake emotion. Can machine recognize real and fake type of emotion, like real a smile or fake a smile?
Oh, I see. Yeah. Okay, so you're saying can I would say that I would think that AI systems can recognize and generate realistic and fake expressions. To me, that's an easier task than doing better than humans on transcription, for example. So I have no doubt that systems that we build can even have superhuman abilities to understand and process human emotion. If that's what you're asking. That's, to me, that's very visual, and I think our systems are pretty good at that. Even analyzing it down to the actual sets of muscles and their patterns of activation someday, where, in fact, I can imagine systems being built, and we've seen this in some areas, like detecting deception in humans, where we build machines that are better than people at doing that, giving us signals in voice and in facial expressions that there's deception going on by this human being that are superhuman. Humans are fooled easily, and the judges are fooled easily, but the system says, watch out, this person's lying.
I think there's one question somewhere there at the back, right? If I'm not wrong. Or if not. Okay, then we'll take this one. Yeah.
Hi, Eric. This is Ankit from Indian Institute of Technology, Delhi. And I would touch upon the topic of trustworthiness on AI. And I think you talked about the sleeping giant. On the health front, AI is a sleeping giant. And on different note, yeah, so Pedro Domingos yesterday tweeted that whether would you vote for a robot for a president? I think, yeah, so on a different note. But the question is basically when we want to put...
Isn't it easier these days?
Yeah.
to say yes to that. Yeah.
Yeah. Yeah, so the question is basically when we want to push these AI systems, especially on the health front, and we see a lot of resistance from the doctors as such, and I have few friends in our All India Institute of Medical Sciences who also agree on that you can't push the AI systems, and they have a lot of restraint, and we have a lot of disconnection from there. And that's why even like in India, this is even more critical, where we have very dearth of doctors and lot of patients and lot of population as such. So how, since you have been on the neuroscience side as well, and you have interacted with a lot of people, what is your take? How these technologies can be pushed to the other front, and how we can convince people that AI is trustworthy on those fronts? And I think you touched on a few topics like HCI and all. But yeah, how to convince the people or the other community who is not an AI community
to go on that. So there's two pieces there. There's the actual, is the system robust and trustworthy? And then can you convince people as such? So let's say there's the dependency there, but there's two separate issues. I think one way to work on what's called the translation of these advances in computer science into healthcare is to point out how poor people are, how poor experts are at making decisions, and also picking the problems correct, picking the problems right. I mean, so we have a student right now working with 40,000 surprising deaths at University of Washington Hospital, working with this UW student. We have all this data, and we want to figure out, okay, why did these patients die when they came in as elective patients to the hospital? Over many years, we have lots of patients that you wouldn't, the surprise deaths. And we said, let's build systems to reason about where was the failure to rescue, it's called in medicine, FTR. Where did it happen? And could an AI system have helped? Well, we're in a situation now where we have deaths in the human situation, and we're looking at where AI could have helped a bit. You can imagine by picking the right problems, the arguments get more quiet, right, in terms of what you're trying to address. Or building systems that are augmenting and assisting, easing the daily burden of a physician, also very acceptable. Oh, I like that idea. Just make sure that I'm making the decisions. That's fine. Let's augment the physician, for example. I think 25 years from now, by the way, I think I said this 25 years ago, but now it's different, hopefully. 25 years from now, I think it'll be more obvious, and it'll be kind of funny looking back in history as to why it took so long to get these inference tools into healthcare, among other fields. Now, on robustness, let me just disclose to the world here that I'm a trusting driver of the Tesla in autopilot. I've had it for a couple of years now, and I've become accustomed to using it. I'm also one of the rare AI aficionados that was almost killed in that car in a stochastic situation that I didn't expect on the same road as usual, where I had $15,000 of damage, 2 tires blow out, and almost severe injuries. A lot to do there.
Okay, we'll take one more question. I think there at the back somewhere. Yeah, if you can raise your hand. Yeah.
Hello.
Yeah.
So I have 2 questions for you. One is about the models of complementarity that you've shown.
Yes.
So there it was shown that like biases, like human, we have some perception, some biases in our mind, and machine learning can complement it. But machine learning itself is data driven, and the data is what has occurred in the past, which also reflects the bias as well. So how can that complement and decrease or reduce that bias in human perception? That's one question. And the second question is one point that you shown in your slides about biodiversity. Like AI is now, like it can be used for biodiversity issues. So I want to know how this can be useful for preserving animals or minerals, because this is also a burning issue. Human can't exist unless they also do exist. Thank you.
Let me just refer briefly to the first question for now, because I want to get to the second one, and just say that humans and machines, even from the same data, learn differently. And that gives you a complementarity opportunity. And typically, I'm thinking of complementarities when it comes to not just biases, but blind spots, inferential abilities, the ability to see different things in a visual image. And so you can imagine rare cases where the same biases are in both, and that wouldn't be a very good situation for complementarity. But you can also imagine studying both. You want to study both sides and understand how to build, in an engineering sense, the complementarity and how to harness it. But it's a good question. The second comment, let me just say, E.O. Wilson, who is a very, very renowned sociobiologist and sustainability person, told me at a very small meeting after coming out of a meeting on AI opportunities in the environment. And I actually asked him if I can quote him, and I actually quoted him at a meeting where I gave a whole talk on the answer to your question, pulling together many pieces of work, that AI may be the only hope for humanity on this planet. I said, that's a very strong statement. Can I say that? He goes, I believe it. He really believes, and by AI, I think he meant not just the learning, the data-centric sciences, and the inference and the planning and the optimization and perception. I think he was also talking about this idea of doing modeling and simulation. It was in his mind, too. But today, in preparing this talk, or last night, I had examples that I was going to pull in to show you exactly what people are doing, in particular Andreas Krauss at ETH Zurich, Carla Gomes at Cornell, when it came to a reservation problem with models about what different species needed to do to survive in their niches, and overlaying the constraints of land ownership, where I could give you back these acres and you'll own the same acres, but can I distribute it differently and put these paths in automatically? and have an optimization system with submodular optimization running and outputting alternate plans with probabilities of survival of species based on the models coming up as well. Very impressive work with a beautiful visualization and display kind of console that lets you interact with the biological models as you optimize in tight loops. And so that's an example of some work going on in this space. And the systems have actually now been used with examples in periods of several years ago now. So people are going back now and looking at their impact in natural park areas and so on. So it's very, very exciting work. There are many other applications also in conservation more generally. Even things like ride sharing done well is a great example for CO2 footprint and so on. So I'll stop there, but thanks for the great question.
Thank you very much for the questions. I'm sure there are more, and maybe we could take it offline. With that, I'd like to thank Eric again and request Professor Narayan to give a small token of our appreciation. Thank you, Eric, for being here. It was great with this talk. Thank you very much. Yeah. Okay.